good morning, everyone, to today's IAgrE Engineering for Food and Drink Special Interest Group event. This is our third event this year, dedicated to powder handling and granular flow. My name is Daniel Heft. I am the chairperson of the group. Today, we're going to have 6 presentations going on. The first presentation will be given by Rajeev Dattani from Freeman Technology, titled Measuring and Understanding Powder Flow and Powder Behavior. A little bit background about Vivek, about Rajeev, sorry. Rajeev is an application specialist at powder characterization company called Freeman Technology, and is based on the company's headquarters in Tewkesbury. He has a master's degree in microsystems and nanotechnology from Cranfield University, where IAgrE actually on campus, followed by an MS in plastics electronics and a PhD in polymer and fullerene solution processing at Imperial College in London. Having joined Freeman Technology in 2017, Rajeev is involved with supporting users of the Freeman Technology's powders testing instrumentation, from initial installation and training to ongoing education and application support. So we're very pleased to have Rajeev here today, and I hand over to you. Perfect.
Fantastic, cool. So thanks for the invitation. So yeah, as you said, Daniel, just a presentation on measuring, understanding powder flow and powder behavior. So powders are used in a wide range of different industries. So here the focus is also on food, agricultural materials, but they're ubiquitous in pharmaceuticals, cosmetics, additive manufacturing. And these powders need to go through hundreds of different types of manufacturing processes. There's many thousands of different types of formulations. And the one thing which is true, regardless of the industry that we're working in, is that the powder characteristics are ultimately what will influence the quality and properties of the final product, as well as how that material moves through the manufacturing process. But even though powders have been used in all these different industries for so many years, powder behavior is still not that well understood. And that lack of understanding leads to stoppages, leads to downtime, leads to materials that don't meet specifications. So ultimately, it's an expensive and inefficient use of resources. But if we can start to measure powder and understand powder flow and powder behavior, we can start to overcome these challenges. So let me just check. Am I showing a PowerPoint screen?
Yes.
Yeah, cool. Just the way Zoom works is a bit odd. So powders themselves are defined by a set of physical and chemical properties. So, and they'll have each particle and each set of particles will have a specific size, distribution, a shape distribution, the particle density, bulk density, cohesive properties, porosity of the particle and of the bed. And each one of these properties gives some contribution to how that powder behaves in process in an application. But powders aren't just the solid particles themselves, they're a bulk assembly that consist of potentially liquids on the surface of the particles, or in the air between the particles as well. And so powders are really a bulk assembly that are dependent on how all 3 states of matter interact. And so if we look at this animation here, we have some powder particles in a vessel, and when they flow from one vessel to another, they might flow in a certain way. And in that process, air could get trapped between the particles. We now have this aerated powder, which when that flows from one vessel to the next, it might flow much easier. It's more fluidized, it's been aerated. If we tap that vessel, so release the air from between the particles, de-aerate, consolidate the sample, it might not flow at all. So we've gone from it's the same powder particles. All we've done is change the packing state, which has then completely changed the flow properties of the particles. And so what we've done there is imposed those different levels of stress on the powder, going from low stress to a high stress state. And when we talk about powder behavior, if we could define this mathematically, we could say that it's a function of its size, shape, stiffness, all those physical and chemical properties which I listed before. but it's also very much dependent on the environmental conditions which we expose that powder to. So is the powder consolidated? Is it aerated? What's the humidity? What stress are we exposing the powder to? And with all these variables, there's no way that we can predict powder flow just from first principles. And as a bit of an example, if we had 12 variables with 4 permutations, this would give us over 16 million combinations. So mathematically, you can see it's a very challenging problem to start to solve. And this is where powder rheology comes in. So with a rheometer, you can aerate a sample using a compressed air supply. You can with various attachments, you can measure the powder's flow energy, and I'll come on to that in the next few slides. You can also compress a powder, measure the wall friction properties or the shear properties. And so with powder rheology and with the FT4, we can measure bulk properties, so density, compressibility, and permeability. We can measure dynamic flow, so how powder flows in confined and unconfined states, how a powder responds when it's being aerated or consolidated, changes in flow rates, as well as I mentioned, the shear properties, so shear cell and wall friction tests. And with these different types of test methods, you can then start to understand what's happening in process. So is there the potential for segregation, attrition, caking? And I've got a case study on caking that I'll present later on. Electrostatics, and what's the effect of moisture and agglomeration. So that the main principle of operation for the FT4 is that a twisted blade, rotates up and down through the sample on a fixed angle and a fixed speed. And what we measure is the torque and force as a function of height. So that the first step to any measurement is to condition the powder. And this is a gentle slicing flow action which cuts into the powder. So this thin edge of the blade slices into the powder. The particles get lifted up and then just gently dropped back behind. And the target is to have a low stress homogeneous packing state. If we then reverse the direction of the blade, now moving in an anti-clockwise direction, so now forcing the powder to move down and around towards the base of the vessel, that's where we start to measure torque and force as a function of height. You can see the blade moving down, forcing that powder to go down towards the base. So we're compacting that powder down towards the base of the vessel. And then we combine the torque, force, and height measurements and express them as a flow energy. So we measure force as a function of height, torque as a function of height, and then those then get combined. So force times distance is work done, so it's an energy. We can do a similar calculation with torque, and effectively by taking the area under the curve, we get a value for flow energy. And this is what we'll focus on, at least for the first case study. To get an idea then of what that flow energy means, if we were measuring samples with increasing water content, going from 8, 10, 12% water content, we add more moisture, we increase we add more moisture, and then that then we have more cohesion, more liquid bridging between the particles. We then see that as an increase in the flow energy because there's an increased resistance to flow. Alternatively, if we were interested in studying flow additives, as you go from A, B, C, as we add more flow aid, these blue particles, we start to find we have a decrease in the flow energy, so there's less resistance to flow. As you add more flow aid, it's easier for the blade to move down through the powder. And we find that C, 1.5%, is the optimum amount of flow aid to use. If, however, we had a change in the primary particle, in this white particle, say a change in surface roughness, the way that the blue additive particles will pack on the surface will be different, and so our response in terms of the flow energy will change. You might still have the same optimum point, but the path we take to get there could be different. So what we're going to now is a case study on caking, and caking is an issue in a range of different industries. It can occur during transport. Typically, also can occur during storage. And one thing which is important to note is that caking doesn't always occur uniformly. There are different modes of caking, and you can have non-homogenous caking, so it's for something like crusting at the surface, or other sorts of hybrid behaviors, mixtures of different types of caking modes. And it's not always possible to investigate and understand this just using some other established techniques like shear cells, penetrometers, or uniaxial testing. By using the dynamic test of measuring force and torque as a function of height, you can then identify these individual caking modes. So the most the one that's sort of most easiest to understand conceptually is homogeneous caking. So here we have, on this graph, we have energy on the y-axis, the height above the base of the vessel on the x. And so this is our blade coming down, and we measure an instantaneous energy, and we see that on day 0 we're much lower throughout. As you go to day 1, the flow energy increases. As we go to day 2, that the energy is increasing there uniformly. If we look at something like SMP, so skimmed milk powder instead, as we go to day 1, we have a small bump, and we go to day 2 in the red, that bump is a bit deeper and a bit taller. As you go to day 3, day 4, that the size and position of that peak is constantly moving. So that we have a crust propagating down through the sample, which is growing larger over time. And we can also have hybrid caking, so where we might see that initial increase in flow energy, as you see for the blue line here on the right hand side for day 1. But as we move to day 2, we now have a crust forming, and we're seeing both now. We're seeing crust formation and some more homogeneous caking throughout the powder bed. So we've got sort of both modes of caking occurring at the same time. So if we just focus in on this non-homogenous caking with the skimmed milk powder, we stored our milk powder at 2 different relative humidities, and we see in both cases we see a similar result in that we have a crust forming. So you have an increase in the energy towards the top of the vessel, so 50 millimeters above the base, and as we go down towards lower into the vessel, we're actually matching up there quite well with what's happening at day 0, so a non-caked sample. By just doing some calculations and some in-depth analysis of the raw data, we can see we can pull out the depth of the crust, so how thick where the crust is, how thick the crust is, as you might expect at the high humidity. So in green at 75% RH, we have a thicker, deeper crust. And we can also just extract the energy just of the crust. So rather than that how much resistance to flow there was just within the crust, and we see it's 75% RH. That's a much stronger. It's a crust which is much more resistive to flow. And then from that we can also extract the strength of the crust. So we can then determine by dividing the energy of the crust and the crust depth, if that crust is purely down to the caked region expanding, or if that caked region is hardening over time. So is it staying in one place, and do we have more? Do we have a stronger crust, or is that crust increasing in size? And we can see that at both levels we have an increase in strength. So that's telling us that the crust there is hardening over time following that initial caking. Similarly, you can do, again, similar analysis for the SME, just looking at 75% RH, where we have the crust initially increases but then starts to tail off, whereas that energy of the crust is constantly increasing. We've got then a different response in terms of the strength of the crust there as well. And you can follow this through day by day, see this initial peak appearing. We see the depth and strength of the crust increasing, but also see an increase in caking down towards the base of the vessel as well. And you can have translational behavior as well, so where powders go between different modes of caking. So initially we see some sort of hybrid behavior where we have a crust formation as well as caking throughout the depth of the bed. But after we go into day 2, day 3, day 4, it's much more homogeneous. You know, there's no real difference in the, we don't have a clear crust formation at the top. Also of interest is could be, say, humidity cycling, so where the powder may have been exposed to a high humidity for a certain period of time, but then when it's, say, being used in a process, the humidity drops and we go back to ambient conditions. And different materials can exhibit different responses here. So we've got some couple of different food flavorings. So with flavor 1, we go from day 0, we see a dotted black line at the bottom. We go to day 3, so when it's being held in humid conditions, we've got a fairly homogeneous caking there. But as soon as that's been dried, we actually have crust formation. So we've got a clear peak at the top of the base, at the top of the vessel, sorry, and that tells us that only upon drying did we get that crust formation at the powder air interface. Flavor 2, on the other hand, similar at day 0, we got that dotted black line at the bottom. We go to day 3 and we've got quite a strong crust formation. And when we go down back to the dried level, once it's had a chance to dry, it goes actually much closer to the ambient conditions, but we do have a slight dissipation of the crust and caking down towards the bottom of the base, closer to the bottom of the base. And interestingly as well, that the skimmed milk powder, after day 3, we had about 30 millimeters. We see a clear peak in energy. Once that's allowed to dry, again, we've got a dissipation of the energy, so that's telling us that there's a increased caking below the crust once it's had that opportunity to dry. So from this study, what you can see is that it's important to be able to elucidate how the caking is occurring, and it's not so clear cut that if you just have, say, you might have one mode of caking, you could have different modes of caking. They could occur at the same time. You can transition between one to the other, and by doing these types of energy measurements and flow measurements, we can really pick out what mode it is that's occurring. This work has been published in Particulaology early this year. So if you wanted more detail on that, you can follow this reference through and find some more detail on what I've just presented there. If I've got a bit of time, I also wanted to go into another case study on filling, so focusing on sachet filling. So sachets are used in a range of different industries, in food, in pharma, and what's key here and important is that the sachets filled uniformly to a given mass or volume, and you have a low weight variation and high content uniformity. If you start to deviate from that, especially in the pharma industry, you could run risks into endangering patient health. And these same concepts can be used in a range of different other filling operations. So whether you're filling sacs, filling bags, capsules, dyes, molds, and so on. So we had 3 different samples here. It is a pharmaceutical blend that we used in a sachet filling operation. So we had sample A gave us good performance. Sample B had a slightly wider particle size distribution than sample A, but was more average performance. Sample C had the same particle size distribution as sample A, but did not perform well in the process. So we've got a good sample, sample A, an average sample, sample B, and a bad sample, sample C. So with by doing permeability measurements on the FT4, and this is via measuring the pressure drop across the powder bed at a fixed air velocity with increasing levels of normal stress, we see that sample C in the black had the highest pressure drop, which means it's the lowest permeability. So that low permeability meant that the powder that was the air that was within the powder isn't able to escape when it enters the sachet. So the air then remains trapped in the sachet, which then leads to a higher weight variation. Sample A and sample B were both gave a lower pressure drop, so a higher permeability. We can also we measure the aerated energy, so that's by passing air through the powder and then doing that dynamic flow measurement. And what we see here is that sample A gave us the highest energy, so that high aerated energy, likely due because it also had higher permeability. The air is able to move through the sample and doesn't influence the powder bed as much, whereas sample C gave a much lower energy, so it's much more sensitive to aeration, sample C, and that can then mean it might be potentially prone to segregation, to dusting, which can then impact on content uniformity. What we see in terms of the basic flow energies at sample A had a much lower basic flow energy compared to samples B or C. So that means that sample A was able to flow much more freely in the forced flow conditions that would be there in the feeding process that then leads to filling. So it was able to flow much more readily. And we also see for sample A much higher compressibility, and that can be that can happen for more cohesive materials, but it can also be beneficial when it comes to content uniformity. And you could expect that to have an impact on the filling process, but because of the low stresses within this process, it doesn't seem to have as much of an effect. So from there, and with all that data, we can then determine a design space for these samples. So we can say that the green zone where sample A lies can mean that powder will perform well. We have the amber zone, so that's where sample B is, and gave us an average performance. And then we have our red zones where that's where sample C lies, and then need to process issues. Obviously, this is just with 3 samples, and you would need multiple samples to really hone in and define where these design spaces lie. So in conclusion for this, the dynamic and bulk characterization tests on the FT4 can pick out clear differences between 3 samples that we know behave differently in process. And it's only by combining the data from all these different methods that we can confidently come up with a design space, and we can match up new formulations against that to know whether our formulations will perform well or not in that given process. So just to summarize, as I'm sure you're aware, powders are complex materials, and no single value will really tell us how that material will behave in a range of processes. You need to approach the problem from different angles with different methods to really pull out that full picture. But by doing so, you can start to then predict process performance and use the knowledge that you already have to predict what will happen in the future. So thank you for your attention, and if you have any questions, I'm more than happy to answer them.
Thank you. So I said, if anyone has a question, put them in the box. Rajeev, did you do any investigation looking between the link of the powder rheology and the flavor delivery itself?
We haven't done that for in the food industry. That would be quite interesting to do, actually, to see how the flow that then relates to how a consumer's you mean in terms of how our consumer then experiences
the flavor, like the perception or the sensory. I was just thinking,
that'd be quite an interesting thing to do, actually. We've not done that, but if you've got some samples that you know have a different sensory perception, then we could definitely measure them.
Yeah, I mean, as that we can pick up on that. I'm sure I can get you plenty of flavor samples. It's not a problem. Anna is asking, did you also measure the water absorption of the different powders after subjecting them to different percentages of relative humidity prior to testing?
So I think they were. I'd have to check back to the paper for this, but I think they measured I think they did measure the water content on the sample. So after, say, doing 75% RH, and then did the measure the loss on drying to then get the water content. And I think it did just correlate in the sense that high humidity led to higher moisture content. but I'd have to go back and check the paper itself.
Okay, Natalie is asking, to investigate the crust formation, would the powder have to be stored in the FT4 vessels? Would you weigh it before storage and input this weight when testing it? Would it be conditioned by the FT4 before storage? And she apologizes for throwing in so many questions at once.
That's right. Hi, Natalie. Yeah, so I'll start at the end. So the measurement procedure itself is that you would condition this. You would load the sample on the FT4, do a conditioning cycle, split the vessel, so you which is what gives us a constant volume, and you would then take that conditioned sample across to your humidity chamber, or however you're storing the samples, and then do the measurement. We didn't take the sorry, I'll finish off what I was saying. You'll then yes, store it in whatever humidity, bring it back to the FT4, and then just do a single test cycle. So you're then not if you did a conditioning then test, you'd break up the crust via the conditioning cycle. So you do a condition, storage, and then test. In terms of weighing the sample, you could do that. I would suggest to do that off instrument. So weigh the empty vessel before, weigh it when it's got the conditioned powder, and then weigh it after the humidity. Just so then you've got that. Because then you have the weight of the vessel, and you can then subtract everything off to know how much the sample weight has changed because of the additional moisture.
Okay, and Barbara is asking, have you guys quantified what the causes of differences in behavior between 25 kilogram bags, big bags, and bulk powders for the same starting powder are? Is this the different caking effect you were describing in your presentation, or?
So I didn't quite get the question. Sorry, could you?
I guess she is asking, like, if you take a 25 kg bag of your powder, or any big bags or bulk powders for the same starting powder, and I guess you get different behaviors once you measure them, if you know whether that's down to the caking effects or if there are other factors playing a role, why these, in theory, same powders just differ based on different bag size.
Yeah, so if you were to say, so that's where you can, if you were to store samples in different bags, in different size bags, let's say your the powder, especially at the bottom of the bag, is being consolidated by different amounts. It's got a higher, if you've got a larger volume or larger mass in your bag, it's the stress being applied will be higher, which can then mean that the material at the bottom of your bag is more consolidated and might flow differently to the material which is closer to the top of the bag. And you could then use similar measurements to what I've described to evaluate what that effect is of how much stress is being applied, or how that stress is being applied.
Okay. I think that's the last question from Amos, given time interest. Amos is asking, any experience with the Brookfield powder flow tester? How do you find repeatability or consistency in powder flow testing in general?
Personally, I'm not had any experience with the Brookfield powder flow tester, but we obviously have some other people here who I think Richard and Vivek who have. So maybe they can have sort of give their thoughts on that. But in terms of repeatability and consistency for powder flow testing, most of the variation that you'll have when it comes to testing powders will really come from the powder itself. Powders are variable. They're not. It's not like they're not standardized really in any way. Any slight variations that you have in size distribution, in shape, in porosity, all these different properties will have a knock-on effect. Taking Barbara's question from before, thinking about that, if you stored the same material under different stresses, without knowing, if you store it under 25 kilo from a 25 kilo bag and take it from a 1 ton bag, the powder there's had different stresses imposed on it, and you can see that historical effect when you come to measure the flow. So you can have materials that give you good repeatability and consistency, but it's very much material dependent as to how that transpires. So yeah, Amos, if we can sort of maybe discuss it offline later on, but I would say it's very much material dependent. I find repeatability and consistency.